Hello, my name is Alif Hamid bin Azhar. I'm going to present about a schematic diagram of a steam power plant. It consists of furnace, boiler, turbine, generator, condenser and pump, and has 4 streams, S1, S2, S3 and S4. S1 is at 600 Celsius and 30,000 kPa at a state of superheated vapor. Enters the turbine and exit at S2 179.9 Celsius and 1008.63 kPa in saturated liquid vapor mixture. Process occur in turbine is isentropic expansion as it converts heat energy from steam into shaft work. S2 enter and exit condenser at 179.9 Celsius and 1008.63 kPa in saturated liquid state. No temperature change of the working fluid as it only change the phase of the fluid. Heat from the phase change is released to the lake. S3 exit the condenser and enter pump and exit at 185.5 Celsius and 30,000 kPa in a compressed liquid state. Compression that occur in a pump is to increase the pressure of the working fluid that drop after exiting the turbine. Stream 4 enter boiler and exit at SS1 at 600 Celsius and 30,000 kPa in saturated vapor mix state. The process occur in boiler is constant pressure heat addition. Furnace supply the heat to the boiler and the water heated up in the boiler.
Hi, my name is Han Jingwei. Now I'm going to explain about the assumption that I assumed when designing the power plant. These are the assumptions that I assumed in the power plant. The first assumption is the temperature and the pressure of the inlet steam that enter the turbine is 600 degrees Celsius and 30 megapascal. This assumption is based on the Mitsubishi Heavy Industry because the turbine made by Mitsubishi maximum can withstand with the 600 degrees Celsius temperature. Besides, it is also in order to increase the thermal efficiency. When we look about the formula of thermal efficiency, which is 1 minus QL over QH. Higher the QH, higher the thermal efficiency. The second assumption is the pressure change in boiler and condenser is negligible. Since there is no work done by or done on the condenser and boiler, so the pressure is assumed approximately to 0. The next assumption is the mass flow rate of the stream is 210,000 kg per hour. This assumption is get by using the ICON simulation software by trial and error method, which give a result if the steam that leaves the turbine has a quality more than 90%. This factor is important because the steam that has lower than 90% quality will cause the erosion on the turbine bed. The next assumption is the turbine is well insulated. This is because the isentropic expansion occurs in the turbine, so it's important that the turbine to be adiabatic so that no heat loss to the surrounding. Furthermore, the power plant is assumed to operate in steady state and there is no leakage between the piping system. This is because it will be convenient to analyze the power plant in steady state because the power plant will operate 24 hours, 7 days, non-stop for a long period. That's all. Thank you.
Good day. I am Nur Hidayah Negdar and I am going to present about the type of cycle adhere to this process. Rankine cycle. So, why are we not using Carnot cycle to adhere this process to? Based on Carnot principles, process 2 to 3 can be modeled to expand isentropically in a well-designed turbine. However, as you can observe from the graph, there is a significant decrement in the quality of the steam along the process. This means at some point turbine will handle low-quality steam with high content of moisture, so water droplets will form on the turbine blades. This will cause a major breakthrough, as it is most likely will cause the turbine blade to erode and eventually cause a major source of wear. Steam with quality less than about 90% cannot be tolerated in the operation of power plants. This can be overcome by using a working fluid with a very steep saturated vapor line. Two-phase liquid vapor mixture from the condenser will be received by pump. Supposedly, to compress the liquid vapor mixture to its initial state, the process has to occur isentropically. However, it is a bit difficult to associate the process with the idea of isentropic compression process. This is because it is not easy to control the condensation process precisely to achieve the desired quality at state 4. Besides, pump is practically designed to handle liquid only. Now, to eliminate these problems, we can execute the process by using Rankine cycle. This cycle is more practical to superheating the steam in the boiler and condensing it completely in the condenser, and does not involve any irreversibilities. The cooling medium we use is lake. Lake is one of the best options for the heatsink, as it has high thermal energy capacity to absorb heat without changing the temperature of the lake, and also as the location of the plant is in Taiping, Perak, there isn't any sea located nearby.
Hello everyone, I'm Nicole. Now I'm going to talk about the data analysis and calculation. Since there are myriad of unknown variables, so we have to get the following data from the icon simulation software, where Q hash equals to 4559.67 megawatt, QL equals to 3184.49 megawatt, WL equals to 1450 megawatt, Win equals to 69.02 megawatt, and the volumetric flow rate equals to 72,499.13 meter cube per hour. According to the data we get, the actual power produced by the steam power plant equals to 1,380.98 megawatt. The amount of coal required for the steam power plant is 182.39 kilogram per second, where we get the heat value for the low sulfur grade coal from the World Nuclear Association 2018, which is 25 megajoule per kilogram. The steam generated by the steam power plant equals to 72,499.13 meter cube per hour, where we can get the value directly from the icon simulation software. The thermal efficiency for the steam power plant equals to 0.3, and the total work required to run the plant equals to 69.02 megawatt.